of stay in one group of people versus a typical length of stay in another group of people. In such instances, people tend to use non-parametric tests, and the Wilcoxon ranked sum test is an example of that. So for small studies, even though the outcome is continuous in scale, if it's skewed, then the Wilcoxon or another type of non-parametric test would be better because it's not going to be affected as much by extreme values. Once your data set becomes larger, there's something called the central limit theorem that says t-tests continue to work well even if your data is skewed if you have big data sets. And typically, a rough rule of thumb is if each group has at least 30 people, then typically the t-test should be fine. But for smaller than that, a non-parametric test like the Wilcoxon test would be better. That's why, in general, I would say answer 3 would be more appropriate. The next question is, if you're looking at an outcome which is a stage of disease, if a person has a cancer, they're stage 1, another person has a cancer, stage 3, what type of outcome is that? What type of analysis would you do? Well, remember, the type of analysis is driven by the scale of the variable. And even though the variable is categorical, stage 1, stage 2, stage 3, and stage 4, those numbers reflect an order, so it's at least an ordinal variable. If those numbers also reflect distance between different stage categories, then you might be able to treat it as a continuous variable. So I would say a staging of a chronic disease is probably ordinal or perhaps continuous in scale. It's continuous if you believe that stage 3 people, for example, are halfway between stage 4 and stage 2 people on some spectrum. Otherwise, you'd be better off treating it as an ordinal variable. That means you'd be doing non-parametric tests. Talked about in the previous. I'd say the answer to this question was 2. The next question says, let's suppose you're doing a study and you have a 2x2 table for your results. Looking at spam eaters versus non-spam eaters, you're looking at an outcome of anxiety, needing a vacation now, like we did last week. And you measure a risk ratio, the risk of being anxious among the spam users versus the risk among the non-spam users. And now you're thinking of the sampling distribution of that measure. Remember, imagine doing many studies like the ones you just did. Now, each study gives you a risk ratio. Now, the risk ratio can be as small as 0. Risk in the numerator is 0. It can be as big as infinity. Risk in the denominator group is 0 because you'd be dividing by 0. So risk ratios can go from 0 to positive infinity in their theoretical values. Well, you tend not to see values of 0. You tend not to see values for infinity. So what it means is you've got more room to spread out towards the higher end of things. Say you did one study and got a risk ratio of 2. You could do the study again with similar people. You might get a risk ratio a little bit bigger than 2, a little bit less than 2. The lowest you can get is 0. The biggest you can get, though, is positive infinity. You get more room to get positive values. So risk ratios tend to have a sampling distribution that has a skewed distribution, with some studies showing atypically large values, just like length of stays have some atypically large values. If you take the logarithm of the risk ratio from each study, that logarithmic transformation tends to pull in the large values. A very large number, take the log of that large number, will still be as large, but not as large. So what logarithmic transformations tend to do is to take distributions that have a long positive tail, length of stay or a risk ratio distribution, and make that tail not so long. It tends to give you a distribution that looks more normally distributed. So the answer to number 2, the quiz question was number 2, and that's going to become important today and next week. We look at odds ratios from models, and we see that the model gives you an estimate of the log odds ratio. The confidence interval is going to be built on that scale. And then the computer will give you the corresponding confidence interval on the original odds ratio scale. So more about this as we go through today and next week. Next question says you have a 2x2 table, but it's from a small study. Which of these tests would you do? Well, 2x2 tables are analyzed either using chi-squared test or Fisher's exact test. Chi-squared test works fine, I said last week, as long as you have enough people in each of your expected cells. But if the expected cell count is, say, less than 5, chi-squared test might malfunction because you divide by the expected number It's a test statistic value for the chi-squared test. And dividing by a small expected number gives you a big test statistic value, which would then tend to give you small p-value. Well, in general, the rule of thumb is if your expected numbers are less than 5, 5 is a very conservative number. But if it's less than 5, then you should start worrying about using the chi-squared test. It might be better to use another test that's more difficult to calculate, but is available, but is appropriate no matter how big or small the data set is. And that's what the Fisher exact test does. So for small studies, people tend to report Fisher exact tests, and that's why I meant to do this question. Let's see. Next question. Oh, that was it. So those were basically questions just to make you think about statistical inference. Some of them will have direct bearing on what we have today. But are there any questions before we move in? If anyone wants to send a chat question, I'll hang on for a second just to try to answer. If you have any questions from any of those things, feel free to do that. Because what we're going to do in a second is we're going to move on now to build on what we talked about last week, which is basic statistical inference, by introducing the idea of a multivariable analysis. And the way we're going to do that is with regression models. So today what I hope to do is just give you an overview of regression models, and then next week talk more in detail about one type of regression model, namely the logistic regression. So let me just move ahead. I didn't see any questions popping up, so let's move ahead to talk about regression models. What I like to do is describe one model that I pulled out of the literature. This is an example of a model that's called the mortality prediction model. So it's developed by an epidemiologist and some statisticians here in Massachusetts, in the western part of our state. And their goal was to come up with a way to assign a number to each hospitalized patients who are being admitted to their intensive care unit, where the number reflects how severely ill that patient is. Because imagine you work in the ICU, the intensive care unit. You have 2 patients being admitted roughly at the same time. And say you're the head nurse of that unit. And you have to decide how much care a person should be given early on, because you have a limited nursing staff at your ability, and you have a certain number of patients, all of which deserve attention, but some deserve more attention than others. It'd be very useful to have a number attached to each person when they're admitted to your unit that describes how severely ill they were or are. And that's what this mortality prediction model is going to do. It's going to try to assign a number that reflects disease severity. In particular, what that number is going to reflect is the probability or the risk that this patient's going to die during his hospital or during her hospital stay. So people with high predicted risks are very sick. People with low predicted risks are not as sick. Well, I'll show you their model on the next slide, but basically what they did is they captured a large number of potential predictors that might have some influence in predicting whether a person's high risk or low risk of dying. And we'll go through this type of analysis probably next week. And they came up with a subset of 7 factors. That's what we have here. These were the final 7 predictors that they included in their models. And these were chosen because in some sense they were the best predictors of the set of larger predictors, the best predictors that gave high risks to people who actually died and low risks to people who didn't die. In other words, these seem to be the important risk factors. And as I said, there are 7 of them. One is a binary variable, which says whether this patient was conscious or not. If they were comatose or in deep stupor, they had a value of 1 assigned to them for that value, 0 otherwise. Another variable assigned to each person was the type of admission. If they were emergency admission, they were coded as a 1. Otherwise, they're coded as a 0. If their diagnosis for being in the hospital was due to a cancer, they were coded as a 1 for that variable, 0 otherwise. If they had prior CPR, in other words, if they were hospitalized before, or if before coming to the ICU, they were in another part of the hospital, and they had a cardiac arrest, and they underwent cardiac pulmonary resuscitation, CPR, they were coded as a 1, otherwise they were coded as a 0. And if they had an infection while they're in the hospital, they were coded as a 1, otherwise they were coded as a 0. Those first 5 variables are all what we call indicator variables. They're coded as 1s or 0s. Ones if they have this condition, 0 if they don't. So the variable indicates having a condition, indicates being comatose, indicates being an emergent admission, indicates having cancer,